Hello, everyone. Ever since the opioid crisis started in the late 1990s, an increasing number of people have been addicted to both opioids and other drugs. This has caused drug abuse to be a significant problem for the new generation. Today, we're here to share the models that we have developed that analyze the destructive impact that drugs have on the user and on the society. In order to develop these models, we had to make the global assumption that new drug use trends and policies do not develop in the future. This assumption was necessary for us to rely on drug data from previous years to predict future drug use. For the first part of the model, we were asked to predict the spread of vaping over the next 10 years and compare this spread to the spread of cigarettes. Our approach involved using high school vaping data to predict e-cigarette use, and then we later compared the smoking trends to the e-cigarette trends based off of the year that both of these drugs were released into the market. One main assumption that we made was that only data regarding high school students was relevant for modeling e-cigarette use. This is reasonable because e-cigarettes are the most prominent among high schoolers. We also assumed that the growth of e-cigarettes began in 2003. And we made this assumption because the first commercially successful e-cigarette was patented in 2003. Here's a plot showing the percent of high schoolers who use e-cigarettes in the last 30 days from 2011 to 2015. We decided to use a logistic regression to model e-cigarette use because there's a lower limit of 0% and an upper limit of 100% to the percent of high schoolers who use e-cigarettes. Logistic equations are in the form as shown to the left. Through algebraic manipulation, we transform the logistic equation into a linear equation as shown to the right, where E of t is the percent of high schoolers who use e-cigarettes t years since 2003. In order to determine the k, r, and alpha values, we varied k starting at 100% and decreasing by 0.1% increments. For each k value, we performed a linear regression in order to find its respective r and alpha values. This is shown as an example for k equals 22.8%. We then used the k, r, and alpha values to calculate the predicted e-cigarette use from 2011 to 2015 for each k value. And then we computed the percent error by comparing the actual to the predicted e-cigarette use. When comparing percent errors, we discovered that a k value of 22.8% yields the lowest average percent error and thus matches the actual data the closest, as shown by this graph. After substituting 22.8 for k, along with its respective r and alpha values, we obtained the following equation. We then substituted 26 for t in order to obtain the e-cigarette use 10 years from now. E of 26 is 22.8, so our model predicts that 22.8% of high schoolers will regularly use e-cigarettes in 2029.
So in the second part of our first model, we were also asked to compare the growth of e-cigarettes to that of combustible cigarettes. The main local assumptions we made here are that the growth in smokers in the United States follows the trend in the growth of purchases of cigarettes in the United States. And we also assume that growth of cigarettes and combustible cigarettes began in specific years. As Amanda mentioned, for e-cigarettes, this would be 2003. And for combustible cigarettes, we assume to be 1900, as that was the most obvious known point to start from, looking at the American Lung Association data. So how we compared these two varying units was by developing a growth proportion ratio. So growth proportion is effectively the difference between the current year's usage and the previous year's usage, and then divided by the previous year's usage. So this function was applied to e-cigarettes using points that we developed from our logistic regression, and also for combustible cigarettes from the American Lung Association. Obtaining these two growth proportions, we divide the growth proportion of e-cigarettes by that of combustible cigarettes to obtain the growth proportion ratio. A growth proportion ratio of 1 would mean that e-cigarettes and combustible cigarettes are growing at the same rate, while a growth proportion ratio greater than 1 would mean that e-cigarettes were growing faster, and less than 1, meaning combustible cigarettes, were growing faster. So we've plotted that growth proportion ratio for every year and since each drug's release. And we found that in the first 14 years of each drug's respective releases, that combustible cigarettes were slower and e-cigarettes were much faster than the growth of combustible cigarettes. But in years 15 and after, e-cigarettes quickly slowed down and combustible cigarettes grew much faster. So in order to validate our logistic regression model, we looked at data from the National Youth Tobacco Survey and found that they determined 20.8% of all high schoolers were using e-cigarettes, while our logistic model predicted that 22.3% would be using e-cigarettes in 2018. So this yields a percent difference of 7.2%, which is relatively small considering our logistic regression only had 5 data points to be created off of. So the strengths of the logistic regression model is that, like Amanda said, it has a carrying capacity of 100%, which is realistic. And it's also rather simplistic as it's also only spans a shorter period of time before reaching carrying capacity. So there's not as much open space for random fluctuation or hidden variables to affect that trend. The weaknesses of the logistic regression model include that the number of combustible cigarettes and the growth of purchases we assume to be comparable or follows the number of consumers in the United States, which may not necessarily be true, as consumers can purchase more cigarettes in another year. And then we also said that tried comparing the entire US population of smokers to just the high school e-cigarette population, which also may not necessarily be well to compare.
So Model 2 asked us to use a high schooler's demographic data, which we interpreted to be race, sex, and grades, and then calculate the probability that that student had used each of 4 given drugs, which are cigarettes, alcohol, unprescribed opioids, and marijuana. Then we apply this model to a class of 300 students to find how many of the students had used each of those 4 drugs. So the main assumption here is that race, sex, and grade characteristics are all independent of each other, even though grades are dependent on all 3. Mathematically, this is represented by the highlighted equation, where D is the event that the individual student has taken drug D, and X is the event that the individual student has characteristic X. We use this equation in our later calculations. So first, we develop a drug probability matrix. This matrix represents the probabilities of certain demographic groups of using drug D using data from the Center for Disease Control. Next, we define a trait matrix, which simply describes an individual K's demographic characteristics. Using the previous assumption and these 2 matrices, we find the probability of individual K having taken drug D is equal to the product of the non-zero elements of the Hadamard product of the respective drug probability matrices and trait matrices. So just go through a problem to demonstrate what that looks like. So we will find the probability an Asian female with B grades has used cigarettes. So first, using Center for Disease Control data, we create the cigarette drug probability matrix. Using our definition of the trait matrix, we create this to be that individual's trait matrix. We apply our equation from the previous slide, and first we take the Hadamard product of the 2 matrices. So here we multiply the elements of the 2 matrices together. So here the red elements we multiply together, the blue elements we multiply, the purple elements we multiply to form the resulting matrix below. Then we multiply the non-zero elements of this matrix to show that this individual has a 1.86% chance of having had used cigarettes.
We then took this function that we created and applied it to a class of 300 high school seniors in order to estimate how many of them have used the 4 given drugs. So first, we took demographic data about the average high school class to create a demographic distribution matrix as shown on the top. Then we ran a simulation in which we generated 300 individuals' trait matrices such that their overall spread of traits matches that of the demographic distribution matrix, and that whether or not they have used a given drug is based off of the probability that is the output of our function. We repeated this process for a total of 10 trials, giving us an average of 36 students who used nicotine, 67 who used alcohol, 38 who use marijuana, and 13 who use unprescribed opioids. To validate our model, we compared our simulation results to a statewide survey conducted by the Minnesota Department of Education. In comparing each of the individual given drugs, we found that the percent difference between the actual percent of students and our predicted percent of students ranged between 8 and 22.2%. A strength of our model is that it is easy to apply for individual students within the United States, in which we simply input their race, sex, and grade point average, and we get an output that is the percentage chance they have used the given drug in the past. However, our model is also overly simplistic, disregarding several factors that are correlated to drug usage, such as income of the student's family, as well as the drug's prevalence, cost, and addictiveness.
Alrighty, so for part 3, we were asked to incorporate both financial and non-financial factors to give an index rating to a illicit substance based on its societal impact. We were then asked to apply this model to marijuana, nicotine, tobacco, and unprescribed opioids. So for this model, we had to make a couple of local assumptions, the first of which being that financial factors are equal in importance to non-financial factors, and this is necessary for the simplicity of the model. Our second assumption was that drug-related aggression incorporates all non-financial factors, such as divorce and domestic abuse. And we can make this assumption because aggression is a primary psychological consequence of drug abuse, which can lead to conflict and violence. So here's our model. We defined M as the monetary cost of a specific drug and A as the aggression score. Again, we can take an average of these to determine I, the societal impact index, because of our first assumption. And here are our results. We obtained the monetary cost to society data from the National Institute on Drug Abuse and our aggression rankings from the National Academy of Sciences. To determine M, we took each drug's monetary cost to society and divided it by the total monetary cost to society of the 4 drugs. Using a similar method with the aggression rankings, we were able to determine A, and again, we took an average of M and A to determine I, the societal impact index. The higher the index for a specific drug, the more negative its impact on society. To validate our model, we used this graph from Vox Media. As you can see, Vox Media found that alcohol was the worst drug, followed by heroin, tobacco, and marijuana. Our model, on the other hand, found that tobacco had the most negative impact on society, followed by nicotine, unprescribed opioids, and marijuana. As you can see, our results are very similar to those of Vox Media because alcohol was the most negative drug, and marijuana was the least negative. And nicotine and unprescribed opioids had intermediary rankings. However, it's also important to note that we approximated nicotine with tobacco and unprescribed opioids with heroin. A strength of our model is that it is very simplistic. As you can see, there are only 2 factors that we incorporated, so it's very easy to apply to other drugs. However, a weakness of our model is that it only determines rankings of drugs and not the degrees to which they affect a society. So to recap, for part 1, we used a logistic model to forecast e-cigarette usage. We found that in 10 years, it reached a carrying capacity of 22.8%. And we also found that e-cigarette usage grew faster than cigarettes at first, but it quickly slowed down. For part 2, we found a function that used student traits to determine the probability that he or she has used a drug, and then we applied it to a class of 300 students using a simulation. Our results were consistent with those from the Minnesota Department of Education. And finally, for part 3, we incorporated both financial and non-financial factors to give an illicit substance, to give an societal impact index to a specific drug. We found that alcohol had the most negative impact on society, followed by nicotine, unprescribed opioids, and finally marijuana. Drugs have devastating impacts on society and our livelihoods, and we must be vigilant in our pursuit of a cleaner, healthier society. Thank you for listening, and we're ready for your questions.
Exhale, you did great, that was good. Okay, so I had a question for you about your approach to question 3. Could you elaborate a little bit more on your aggression rankings and where that came from? You gave a reference, but maybe what was behind those scores?
So for our aggression rankings, it is difficult to find data, like quantitative data for aggressions, to model aggression. But we decided to read a study, and then based off of how the study describes the severity of each drug or aggression, that's how we ranked it based on like 1, 2, 3, 4.
Hi. On page 19 of your presentation, you put the calculations of your probabilities. Is that the same as what you had in your paper?
Sorry, it's lagging.
Yeah, we are assuming the independence, and you can multiply those terms.
This slide?
Yeah. So in your paper, you were talking about the probability of D given x1 and x2. Is that correct?
Yeah, I believe that's correct.
Okay. Could you talk about the differences you have here and why you're making these assumptions about independence?
So we made our assumption that race, sex, and grades are independent, primarily so we could better simplify our calculations. We specifically used Bayes' theorem of conditional probability, and we found it's an easier process if we made this assumption. We assumed that race and sex were independent because they're both genetic, so are therefore independent of each other. And we thought that grades are independent of the other two because of equal educational opportunities. I'm sorry, could you repeat your question?
I was just wondering if you could compare this expression here with what you had in your paper and if they're not the same.
Yeah, so in our paper, we didn't include the original expression because we felt it would be too complicated to list on the screen. So instead we rewrote it a little bit so it could be more easily visually expressed. But we believe that they represent the same mathematical idea.
So when you did your comparison to vaping with traditional combustible cigarette use, so for traditional cigarettes, there was definitely this increase when they were first released on the market, and then eventually there's been a decrease, in part perhaps because people have figured out the negative health effects. And so it's possible to think maybe that what we've just seen with vaping is the same thing, where there's this big increase. In your model, it's just going to be a level out and it stays, theoretically at this 22% over time. Do you think that it's possible that it's going to go back down as we learn about the negative health effects, or do you think that it's probably going to level off? And if so, is the 22% what you would expect if you went out 20 years, say?
I think it's very possible that the number of, or the e-cigarette usage would go down in high schoolers. However, our future works probably would like to address that problem, but in order to more simplify and just restrict the model to a logistic model, we simply said that in our global assumption that no government action or policy will be taken or implemented, so that this number or figure wouldn't really go down, considering if there was actually no action taken to disprove or prove that e-cigarettes were harmful to people.
Just to follow up, I guess, a bit on what Dr. Bliss was asking. So in the 2 months since the challenge weekend, have you thought of any, how you could have done things differently, any things that you would change now, any different approaches to the problem?
Yeah, so in our model too, we only included 3 factors, and specifically race, sex, and grades. So we discovered when we were participating in the competition that family background had a major impact on whether a person would be addicted to drugs. And we discovered that a person who came from a family background with drugs would be 8 times more likely to be addicted to that drug in the future. And we did try to incorporate that into our model, but just given the nature of our model and how it requires those conditional probabilities, it was very difficult to find data. So we would like to find some way to incorporate that in the future.
And another thing we would like to add on to is in Model 3, we assume that the monetary impact of drugs is the same weight as the non-monetary impacts. If in future works we would like to find a way to weight the two factors so we can see how the two factors would interact better.
Thank you. Congratulations again. Good job today. Thanks.